So I did a computational investigation of N and P-type doped silica. The applicability of this is that silica can be doped either with electron donating or electron accepting atoms to be used as extrinsic semiconductor. P-type semiconductors have high concentrations of holes that cause them to kind of draw electrons, and those are usually doped with either boron or aluminum, and N-type semiconductors have higher concentrations of electrons, and those are usually created by doping with phosphorus or arsenic. So these are what my models look like. The coloration isn't uniform throughout all of them. I did the P and N-type dope in the corner with silica and aluminum, and then individually just dope with either silica or aluminum, and then just the bulk silica, and again noting that the coloration isn't uniform. Mostly I looked at density of state laws to kind of look at the difference between the valence band and the conduction band to kind of get an idea of what the band gap would be. You can see for this first page, I'm just showing the difference in charge when they're the models. Each of them, we're looking at the N and P types, the dope with aluminum and then dope with phosphorus, and the neutral model, a cation model, and then a anion model. You notice that for, I guess this is not showing. The N and P type model, the band gap is the smallest. Also, that as we increase the charge, it doesn't necessarily affect the valence band and conduction band all that much for just one. So next, I heated the models. Again, there's not that much change between just the P and N type separate models, but for this model, we can see kind of change in the valence band as the heat increases, which was a little bit interesting. And then I did some partial charge density to kind of see that this is unheated and then this is heated. So when you increase the heat, you can see that, as we saw before, not necessarily the conduction band, but the valence band's altered as you increase heat. Then I looked at the excited state for exciting each of the models. Again, there wasn't necessarily that much change for the individual aluminum and p-dope models. You can see there is a little bit addition in the band there, but more interestingly, kind of the change in the valence band of the N-type and p-type models. Also, I looked at changing the spin. Spin would just be having a difference between the spin up and the spin down orbitals. There's not that much change between the models. The difference or amount in spin up and spin down, it seems to stay relatively the same. The only interesting one that kind of came out is this, that we see a change in the valence bands, where most of the other ones kind of retain the same shape. I also just looked at spectra. There was more that I could do with this one. Unfortunately, I wasn't able to finish it. We can see that the P and N type models are a combination of both the individual P and N type models. So there's some interaction there, but it's not a lot as far as the absorbance. Lastly, I made some models. The most interesting one I'll show is the 901. Unfortunately, I didn't zoom in as much, but at some points you can see, not very well in this one, but some of the bonds will break and then reform, so that's a little bit interesting. Lastly, in conclusion, through model being for computational investigation of these models, we were able to use it to get an idea of the effect on band gap by different altering the models different ways. So.
Okay, thanks, John.